All right. Well, everybody's still getting a couple people jumping on. I did want to make one quick announcement for those of y'all are on here. I've received, and some of y'all may have gotten this email, some of you might not have, and in light of what Dr. Pandit is going to be talking about today, I think it's important. I've received a couple of emails and inquiries about bird flu and what the thoughts are about it and what kind of research people in the UCHFAR might be doing, who kind of has jurisdictional authority on how to manage this. What's the likelihood it gets into humans and how bad could it be? Is it going to be the next pandemic for humans? They've been reading news sources, whether it's NBC, CBS, CNN, Fox, and they don't know what to believe. And then how safe is food products? What I'm asking, if you want to participate, feel free to send it to me, but we'd love to issue a couple of kind of one-page summaries or thought pieces about this. If you have some work or an infographic on research that shows effectiveness, who has jurisdictional authority, or it could be a Q&A where you've had some questions that you want to provide answers to, but we'd love to be able to kind of share those with our listserv, which is about 1,500 people. I think if I'm wrong, Marcy can correct me in a minute, that aren't just in the UCHFAR, but industry and other academics, and also share on LinkedIn and eventually get that up on our website. And we'll tag you appropriately in LinkedIn and your college and your industry or whatever it might be, so you can get credit for that. And if people have questions, they can also ask you, which I hope they do. So bird flu, if you've got a one pager or a thought piece you'd like to share, we'd love to share that, publish it, and give you credit for it. No charge whatsoever from us. We want to advertise the great work you all are doing. So please reach out to me if you have an idea of that, or Marcy. We'd love to share your work and show what some of the scholars in this group are doing and how important your all's work is to battling some of these pandemics. And speaking of pandemics, you did not come here to listen to me. You came here to listen to our guest speaker, who is an assistant professor of veterinary epidemiology at UC Davis. And he is going to be discussing innovations in animal health surveillance, the area of climate change and pandemics, which is highly tied into what we were talking about today, a little bit with bird flu. I'm not going to do his all the fabulous work he has done justice. So I'm going to turn it over to Dr. Pandit and let him begin to provide us with some great insights, and open for Q&A there at the end. And if you have questions to type in the chat, Marcy will be able to handle those. So the show is yours.
Thank you, Josh. Let me just start sharing my screen. There it is. Wonderful. Is everyone able to see my slideshow correctly?
Yes, we can see it. Very good.
Yeah, so thank you so much. First of all, I would like to basically thank HFAR for setting up and inviting me for this webinar. I'm really excited to share my work. And as Josh briefly mentioned, I'll be talking about how we are trying to improve and get more insights from doing additional and more targeted surveillance in different animal populations, so that we get better insights, first of all, about animal health itself, and then also about public health issues that might arise from diseases that are transmitting within those animal populations. So especially keeping in context the climate change and the pandemics that we have been facing, I think this is where some of our research kind of mostly focuses on currently. So to begin with, what we basically do is we try to kind of get insights about pandemics and where they might come from, especially from wildlife animal populations. Then we also focus a little bit about climate change and how that might affect the risk of diseases coming from animals, especially because we know that climate change is not going to only affect us, our ability to produce agriculture, but it's also going to affect various animal species that are harboring some of these viruses, and that really changes our interactions with them. And we are expected to see different kind of interactions as the climate really changes drastically across the globe. And eventually, I'll give a brief insight about some of the innovative surveillance platforms that we have been working, especially here in the US, where we focus more on wildlife rehabilitation centers and what kind of insights they can provide us in terms of upcoming disease outbreaks, of course, in wildlife, as well as its implications towards human health and ecosystem health in general. So I kind of have divided my talk into these three kind of big sections as we move along. So let's begin with how we are thinking about generating next generation of predictive intelligence, especially to understand and gauge where the risk of pandemics might be. And as we have been just speaking about the current avian influenza, which is almost a pandemic. It's definitely a pandemic, I think, from my perspective in animal populations. There have been so many other large-scale animal outbreaks that we have been seeing within last decade, including African swine fever. Of course, COVID was a great example of pandemic that happened in humans, and then previously as well with emergence of Zika, Ebola outbreaks. The examples are many. I don't probably need to go into the importance of some of these zoonotic pathogens, but the way we are thinking about this is we're trying to see what might be the evolutionary trajectory of a particular virus that is maybe, let's say, currently circulating within animal populations. And we've been trying to come up with a framework that kind of helps us identify these early warning signals between these animal systems. For example, you can start thinking about the first stage where a particular virus is only circulating within wildlife reservoirs. Then you can think about the primary spillover that might happen just out of chance, just out of any kind of exposure that happens to human population, just because of certain activities that humans are doing, or some kind of a new interaction that happens within those between humans and wildlife reservoirs. Eventually, we start seeing shorter outbreaks, and a wonderful example is actually the Ebola outbreaks that happened earlier, where you would see smaller outbreaks, and those outbreaks would kind of die off after few transmission chains between human beings. Then some pathogens kind of start establishing themselves as human viruses. You start seeing prolonged outbreaks, and eventually some viruses are able to sustain human-to-human transmission, leading to establishing themselves as human pathogens that probably don't need any spillover event to happen for any kind of outbreak to sustain. So let me go back to the previous slide and give a brief overview of some of the work where we are on all our different systems that I'll talk about. We're trying to identify early warning signals between these stages. So are we able to identify whether there is some kind of unbalance or a lack of homeostasis happening when the transmission is circulating within wildlife reservoirs only? Are we seeing increasing primary spillovers from animals into humans? Are we now seeing more prolonged outbreaks for certain zoonotic viruses? And those are the early warning signals that we need to identify, and that's the intelligence that might help us eventually to at least prevent or mitigate some of these pandemics that might happen in the future. So the first example is basically for flaviviruses. And some of this work actually started when the Zika virus outbreak happened in South America. Zika virus itself is a flavivirus, and flaviviruses are a large group of zoonotic viruses that are found all across the world. And the map on the right side actually shows important public health zoonotic flaviviruses. and the location on the map actually kind of shows where they are known to have public health significance, basically, or we tend to see human cases in those regions from those flaviviruses. Those who don't know much about them, they are mostly arthropod-borne viruses, so mosquitoes and ticks. And as you can see, I mean, the main question that we started thinking about flaviviruses was like when it or emerged in South America, we were worried that some of the species that are already there might actually act as a reservoir for the virus and establish the virus circulation within those wildlife populations. And that is actually a problem for long-term mitigation of these viruses or outbreaks from these viruses, because then there is um, uh, always a possibility of spilling it over back into human population, which can lead to additional outbreaks. So the question that we actually had was, can we identify some of these hosts that the Zika virus might establish itself? So we started looking into the established literature data and identified what we know about all these hosts of all these 30 odd flaviviruses, the wildlife hosts of flaviviruses. And we started looking at their macroecological characteristics. And those macroecological characteristics are kind of described here in the slide on the left side. Basically, what do we mean by those macroecological traits is what's the physiological nature of that particular species, what are the ecological characteristics in terms of the type of habitat, diet preference, do they share do they live in a region where there is a high mammalian diversity, high avian species diversity, so on and so forth. And using those, we built up a machine learning model that kind of helps us predict the missing hosts of all the flaviviruses, the 30 odd flaviviruses that were part of our model. And that helped us kind of come up with a distribution of predicted host species for groups of flaviviruses. For example, on the left side, the map actually shows a model that helps us predict um, missing hosts of yellow fever virus and Zika. And you can see that the regions with the more the redder the color kind of shows the higher diversity of predicted hosts based on the model. And definitely in the South American region, you can see that there are some specific regions that might actually host about 9 to 10 species that are good candidates of being reservoirs for yellow fever and Zika virus. Similarly, just want to give a quick example of Japanese encephalitis virus. We definitely know that there are some species, especially the hotspot. We expected the hotspot to be found in Southeast Asia, but we were actually surprised to see a predicted hotspot within the southern part of Europe. And at the time of the models, that when we published these results, uh, there was no report of Japanese encephalitis human cases from Europe. However, there was just one report of mosquitoes being found positive in the southern part of Europe. That kind of raised some concerns around possibility of presence of both the vectors and the vertebrate hosts that can actually sustain the transmission within those regions. So why these kinds of studies are important? It helps us develop basically targeted surveillance for wildlife. Before the modeling exercise, we know very little bit about the known hosts of these viruses. Now we have a nice still targeted list of possible hosts that we can go out in the wild and do additional surveillance around. We know what kind of taxa we need to target. So for example, yellow fever and Zika, we definitely think that primate species might be an important target. For Japanese encephalitis, along with other known species, Passerine birds might be an important group of vertebrate species, and for dengue virus, along with, of course, primates, the other important group might be different types of bat species, especially in the South American region where the bat diversity is tremendous. So that kind of takes us to our current work, where now we are trying to see whether some of these hosts are really a competent host or competent reservoirs in terms of enabling transmission from one individual to another individual. And just to give you a brief background, what competent means is, especially for West Nile virus, many birds and mammalian species actually are dead-end host. What do we mean by that? Is basically once that individual gets infected, they actually don't generate enough viremia to kind of transmit to another susceptible individual. So for the transmission cycle, actually they are the dead end host. And what really concerns us is a host that might be able to enable transmission from one individual to another. So that difference is quite evident across different bird species. And we are now working on a model that actually looks at phylogenetic distances between different bird species along with the ecological traits. And we are now able to predict the distribution of competent reservoirs, competent avian reservoirs for West Nile virus across the northern Americas. And that's basically on the right side, a box plot that kind of shows family-wise distribution of our model predicted competency for avian influenza. Starts with shrikes, a group of birds, passerine birds, tend to have an average of really high competency, followed by crows and jays, which kind of follows pretty well with the observed competency, especially in crows and jays, which we know are really good competent hosts for avian, not for avian influenza, for West Nile virus. So these types of models eventually can help us build additional mathematical models that can help us kind of demonstrate how some of these viruses can sustain themselves within different communities of birds, as well as different communities of other birds and humans, I would say. Now I'm going to change the topic a little bit, and I'm going to talk about one of the studies that we published last year, where we tried to understand how we can predict zoonotic transmission risk of newly discovered viruses, where we are now trying to see if we can really predict the evolutionary trajectory of a newly identified virus from just circulating within animal populations to even moving towards becoming a zoonotic virus as it finds ecological opportunities to infect human beings. So this was some of the work that was part of USAID funded Predict project, where a large consortium of partners actually worked across 60 labs throughout the world to survey bats, non-human primates, rodents and shrews, birds, some domestic animals, some additional wildlife taxa, as well as humans that are very close to these wildlife populations, to identify novel viruses from these 5 virus groups that are listed here on the slides. And throughout these 10 years, more than 900 novel viruses, animal viruses, were identified from this global exercise. However, none of these novel viruses actually were found to be infecting human beings that are living within those communities. So we wanted to see what risks some of these viruses pose to human beings that are living in very close association with these animals. Still, they haven't been found to expose to those viruses yet. So we took an ecological network-based approach to understand zoonotic risk. This actually was a data-driven mostly data-driven approach that kind of helps us quantify zoonotic risk, especially because the previous work was more of an opinion-based ranking of novel viruses, where in 2021, the authors of these studies actually did interview a lot of like a huge number of experts and created a metric that the opinion-based metric that can help them rank those viruses. So with this network-based approach, we wanted to have more data-driven approach that can help us do that without getting biased by anyone's opinions. So we built actually host and virus networks and assumed that these networks will actually work very much similar to social networks. And the missing links or the missing connections between that network will help us understand the potential of these viruses, the zoonotic potential of these viruses. So let's take a quick example. Let's say these are the five viruses that we have, and they are connected to each other when they are found in the same vertebrate host. And the color actually do represent the type of host that they are staying. So the question is that if we found a new virus, new flavivirus that shares a host with yellow fever virus, what is the likelihood that it will also share a host with West Nile virus? And that actually helped us create a network. This is the real data, a network that was generated based on the real data, and the dots do represent known viruses that are both zoonotic and non-zoonotic in nature, represented by the dots or the nodes in the network, and they are connected to each other by sharing of vertebrate hosts. And since there are so many links, you won't be able to see those links in depth unless you really zoom in. But those gray regions are actually because of the links that are connecting them. We built a couple of models. One model that can help us predict whether the link is present or not, and the other model that will help us predict what type of link is there between those nodes. So whether it's a non-human primate link, whether it's a bat link or a Chiroptera link, or whether it's just a human link. And that is an important indication for us to kind of get an idea whether this might be a zoonotic virus or not. After training that model, we did predictions for the novel viruses that were found during the surveillance process and created a predicted network. So now the network on the right side do kind of represent how those new viruses represented by blue dots will behave in that network. And once we have a network representation that gives us key metrics, key matrices basically to quantify the zoonotic transmission risk for those novel viruses. Along with that, we also we were able to generate predictions for 531 novel viruses, and along with that, we also are able to kind of look at their network properties. And the network properties, the simplest one that I can explain here are the degree distribution and betweenness centrality distribution. And the degree distribution basically simply means that how many connections a node can have in the network, and that do represent how many possible hosts that novel virus might have in or might be able to infect. And it is very well known that most of the zoonotic viruses tend to have higher number of hosts that it can infect. Similarly, the betweenness centrality is another representation of how that node is well connected within that network. Also, an important characteristic that helps us determine the host breadth of that particular novel or any virus, basically. So we were able to come up with larger ecological inferences for these novel viruses. And along with that, we were able to come up with a prioritization score that helps us prioritize further studies, especially to understand zoonotic risks for these novel viruses. And if we were to kind of compare the prioritization score for known zoonotic and non-zoonotic virus, you do see that there is the prioritization score for zoonotic viruses significantly higher than the prioritization score for non-zoonotic viruses. Finally, I'm just going to show you the prioritization score for the novel viruses that the model was able to predict for. And these are the top 10 coronaviruses found in the Predict project that had the highest prioritization score, and the bottom five at the very bottom of that plot over there that shows the difference between those viruses. Just want to give a brief kind of caveat here. These are not probabilities. These are not probabilities uh, of being a zoonotic virus. This is just a score that kind of helps us relatively compare viruses for with each other, basically, rather than probabilities. So these types of studies actually helps us kind of get ecological insights. We found that lower centrality measures for novel viruses compared to recognized or known viruses. So we do think that the novel viruses were more host specific than the recognized viruses. And even within novel viruses, novel coronaviruses were predicted to have greater number of species that they can infect compared to other novel viruses from other viral families. And of course, the prioritization score is what we kind of eventually were able to build for all these viruses. Again, it's really important for us to start quantifying some of these risk matrices, because we as more and more surveillance goes into identifying novel viruses, we will be inundated with new virus data, and we need tools that can basically help us help us process this data pretty quickly, and that is very much data driven. So we think that some of these models, as we improve on them, will become a great tool for further prioritization of these viruses, especially because we can now start building in additional predictive features, such as how their genomic whole genomes kind of line up. Can we build some natural language processing models based on some of the large language modeling that everyone's doing nowadays? And that can help us even identify not just the ecological traits, but also the molecular mechanisms that help these viruses infect multiple species, and what type of mutations might lead to increased risk in zoonotic transmission. So some of the future work kind of will focus on improving some of these models with inclusion of predictive features from whole genome sequences from these viruses. Now, moving on to another important topic related to climate change, I'm kind of going to give you a couple of brief examples for some of the work that we do, especially in the public health realm, as well as in the animal health aspects related to climate. And one of the projects that we are doing over here is to kind of build climate sensitive models for arenaviruses, which those who are not much aware about arenaviruses, they are actually viruses that are found in rodent species. Again, in old world and new world arenaviruses, those are the two different groups of arenaviruses, and they are often identified as high consequence agents by different agencies, including CDC, NIH, even UK Health Security Agency. And examples include Hunin virus in South America, Machupo virus again in South America, that have been cause of concern for public health importance, as well as, of course, the very well studied Lassa fever virus in Africa. Even though they are actually um, transmitted directly from rodents, we think that they are climate driven and climate sensitive because these rodent species are highly sensitive to climate changes and the changes that happen in their habitats due to the large scale climate changes. So I'm just going to give you a brief example of two of these arenaviruses. The first one is a Hunin virus, and the plot over here actually shows how how the distribution range for its reservoir species or the rodent species would change in a moderate climate change scenario, which is RCP 4.5 in 2050 and 2070. The map is, those who are able to recognize, is actually Argentina and the nearby region in South America. And blue color actually represents the contraction of the range of that particular species, while the red region actually represents the expansion of that species in that region. And you do see that we expect the rodent species to move away from its current distribution to the outskirts of Argentina, and if possible, if geographically possible, even in some parts of Chile, but more concerningly in the southern parts of Argentina. So this is just with a moderate climate change scenario. With severe climate change scenarios, I think most of the Argentina might not be a suitable environment for this species, mostly pushing some of these species to the northern regions of Argentina and in the northern countries adjoining Argentina. So that actually then helps us kind of not just identify where the species might be present, but also identify what's really driving the distribution of some of these species. And on the bubble plot on the right side, on the left, the y-axis do represent different predictive models that we have, and on the x-axis actually we can see that there are the predictive features that we have over there. And you do see that, of course, the annual temperature, the type of land, especially pastures, are kind of indicative of where the species might be. Urban land is another good indicator whether the species might be present there or not. And along with that, of course, precipitation seasonality is another important characteristics. The map on the left side actually do show a distribution overlap of high human density with highly predicted presence or absence of that species. And those basically hotspots represented by blue dots and the red dots are actually regions where we expect to have high interaction between humans and rodents as the climate changes. The previous map was actually the current scenario. This one's also the current scenario of the hotspots and interactions between those two species. And as we expect the climate to change in the moderate climate scenarios, we expect the hotspots to change of interactions between humans and that particular rodent species to move further away, and more increased interactions in the northern regions, especially for the moderate climate change scenarios in 2050 and 2070. So that kind of helps us understand how much interaction we might see and how the risk would change for that particular disease. And similarly, we just a quick example of how the risk might change for another arenavirus in South America called as Guanarito virus. It is kind of it is transmitted by these two species. And with 2050, the current distribution actually is shown on the left side in the northern parts of the South Americas. However, we do see like increased hotspots of interactions for both the species in 2050, even with a moderate climate change scenario. So this not only helps us identify what are the regions, but also will help us identify what risk and how many expected outbreaks we might be able to see as the climate changes. So that's some of our current work, especially led by my postdoc, Dr. Kulkarni, and along with just predicting um, the scale of the outbreak, we are also trying to build the economical aspects around those outbreaks to see whether responding or mitigating those outbreaks right now might be a better economical decision compared to responding to them later in 2050 or 2070. So some of these modeling tools will be built on the current work that we are doing. Again, changing my gears a little bit, because I thought there might be some audience here who might be more interested in just trying to understand some of the work that we do related to livestock. And here I'm just presenting an interesting predictive model that helps us understand the risk of bovine respiratory disease and how that's kind of associated with climate. So here, bovine respiratory disease is actually caused by it's actually caused in calves, and it's a multi etiological disease where multiple bacteria and viruses might be responsible for causing the BRD in calves. And you can see that we actually did some data collection within different dairy herds within northern and southern California. Those are kind of approximate locations represented by the star. And the hypothesis was whether the cumulative climatic conditions of last 2-3 days kind of lead to increased incidence of bovine respiratory disease in those calves. And can we predict that? So we did multiple models, which included predictive features related to the age, of course, the region, season, and temperature for last 2 days, last 3 days, relative humidity, and temperature humidity index as our predictive variables. And just showing how kind of some of our model results kind of came out, where here you can see uh, these are partial dependence plots. On x-axis, you're seeing the age of our calves. And here you're seeing different regions and different seasons. So as the age changes, let's start with the very first plot on the left side. On the top, you would see that basically the risk of BRD changes in winter on the Northern California is completely different than how it would play out in Southern California. Similarly, uh, similarly, there are similar results that can help us predict what really is driving, especially in terms of the THI, or the temperature humidity index, and the relative humidity, and what leads to increased incidence of BRD within within these cows, and how it differentiates between northern and southern California. So I'm going to move on to the very last section, where I'm going to talk a little bit about our passive surveillance platform called as Wild Alert. And it is actually an platform that helps us, it's basically an early warning system for wildlife health events that can help us identify morbidity and mortality events that are happening in real time within wildlife populations. It is a work that is a really collaborative work between EpiEcos, an organization from Arizona, Wildlife Neighbors Database Project, another NGO that works on a database related to wildlife morbidity and mortality event alerts, and UC Davis. And we have been now active with this platform currently in California, in the state of California, and in the state of Florida as well. So as I said, this system actually works on a database called as Wildlife Rehabilitation Medical Database. So this is a database for managing patients or wildlife rescues that come to different wildlife rehabilitation centers across the US. And you can basically manage the patient records with this particular database. What Wild Alert does is actually it uses natural language processing models to see what syndromes might be present within those animal species. And once it does that, we also run additional anomaly detection algorithms or time series models to helps us identify anomalies between different groups of animals and different syndromes prediction. So that's kind of the overall structure of this early warning system. And just to give you a brief example, these are the 10 on the right side in the table. You can see the 10 different syndromes that the model can predict with a great accuracy, everything almost greater than 90%, with precision and recall. And on the left side, you see the confusion matrix between what really is predicted and what really was the true syndrome associated with those cases. And the diagonal do represent the accuracy over there. So just want to give the latest model stats over there, which we ran in April 2024. And as I said, we are actually active in California and Florida, and this is just a representation of cases from last five years in California, with the bigger dots representing the rehabilitation centers that are active. And now we have you can actually go in and create your like basically you can create a combination of species and syndrome and set up a target that you want to kind of follow up. So for example, neurological cases in raptors, or neurological cases in a group of birds like doves and pigeons, or just one species like skunk, or physical injury in deer. And that helps us create a syndromic surveillance platform, which is now online, and you can just create your own account. It's free of cost as well, and you can create your own search targets. So for example, this is just a screenshot of a target related to marine birds and not associated with any specific clinical classification. And you can see the data, you can see the visualizations associated with the data. And whenever there is an anomaly detected, you actually get, for that specific alert, you actually get an email alert in your account. And of course, you get an alert in your Wild Alert account as well, that there is the threshold has been exceeded and something might be going on. But that is just of early alert. And what we actually do now is we once the system kind of gives us a statistical anomaly, that's what everyone would get an email alert from. And there is an initial communication with those account holders or stakeholders. We actually on our side do secondary internal assessment of what really is happening, whether is this a false alarm, or is there something similar happening in the nearby region. We do additional statistical assessment of that particular anomaly, and then we do further communication, either to report to state agencies or to report that particular rehabilitation organization, or and so on and so forth. So with this process, we have been able to actually identify known threats to wildlife, such as different toxicities, different infections, of course, oil spills here in California, including zoonotic diseases such as outbreaks of West Nile virus in Cooper's hawks, lead poisoning, so on and so forth. But we also have been able to identify emerging threats like the paramyxovirus in Eurasian collared doves was first identified through our system alerts, and another parasite, Sarcocystitis calciae, was also identified through alerts. So it kind of is an additional situational awareness tool for right now. Most of our users are the state agency researchers and people working in state agencies, and it kind of as a cost-effective complementary tool along with their current surveillance efforts, basically. As I said, we are active in California with those blue dots centers contributing their data from those blue dots. We are active in Florida, green dots. We are working on building one for Arizona, and we already have data coming in from other centers all across the US, shown in the red dots. So there is a great chance for our expansion across the country as well. So that kind of almost brings me to the end of my presentation. Um, just want to give again a brief overview of what we are doing. We're trying to look at what might be the early warning signals in animal populations, try to understand that risk with respect to the climate change, and then building up on these other surveillance platforms that can help us really actively respond to some of these outbreaks. As I said, most of our AI and ML methods are used for prediction. As an epidemiologist, we try to go from associations to causation, which is a very hard effort when we are using machine learning methods. But at least that can help us build some decision support tools as we move along. So that kind of ends my slideshow. Definitely more than happy to take additional questions or just jump on to the discussion as needed. Thank you.
Thank you. That was wonderful and super informative. When I think climate change and some diseases, and you probably have read the book, but I don't know, Lost City of the Monkey Gods. I don't know if you've read that or not, but
No, I've heard about it. Yes.
yeah, where they come back with leishmaniasis and how it's starting to creep into Texas and some of the southern states. I always think, well, this isn't good to say the least. So we're going to open it up for questions. If you have questions, I think you should be able to. Marcy, do they have the ability to take themselves off mute?
Yes, they do.
Okay. Yeah. So feel free here to ask questions, and we'll listen in, because I know you all probably have way better questions than I do. So feel free to ask, or if you don't want to ask, type in the chat and we can read in the chat as well.
I was asked one question, if the slides will be sent out after the presentation.
We can do it. Could you send me a PDF and I can
Yes,
send
yeah,
them
I
out
can
to the
do that.
recipients?
Yes.
Okay, that'd be great. So back on your slide with your word graph there, is that just the number of times you see those words come up in research?
Oh, yes. Yeah, that was just like a scrape from journals associated with One Health, and what are their keywords basically.
Okay.
Yeah.
It's a comment there. Fascinating work. Yeah, it was interesting. Are you starting to see with your last bit some multi-state, other region collaborations, people wanting to employ some of the stuff you're doing?
Yes, so certainly, I think with a wild alert, we're trying to communicate and gauge interest across different states. Uh, there is a lot of interest from Northeast states, like especially Pennsylvania and northeast of that. We just hopefully we'll be able to kind of start working there and establish some of these methods, and mostly not just expanding the wild alert as well, but integrating other data sources. So this is just one representation of the data from wildlife rehabs that are coming in, but the state agencies have different programs, hotlines, active surveillance that is going on. So we are hoping that as we expand, we'll have ability to kind of process the other sources of data as well, which will improve our prediction capabilities.
Okay. Yeah. But obviously, typically more data is better to help out. Here's a question here from Philippe. If I mispronounce your name, I apologize. Is this an app that could be used by other research institutes in other countries?
So There are actually the wormed database is actively managing data from other countries. I know there are quite a lot of data points from Germany, England, Australia, and New Zealand. However, we haven't established the wild alert component after that. So, because first of all, sometimes we are not sure whether the data is enough representation of the overall situation, and especially for countries like Germany, where most of their data is in German, we don't have the capability to translate that right now, so into English.
Now, speaking to the app thing, and I'm not telling you this would be, but DHS just yesterday, and I think I'll put it in the chat here just so people can see it. Let's see if I can put it in there. Oh, here we go. Released this yesterday. The Small Business Innovation Research Program, specifically designed for Homeland Security, the Office of Science and Technology and Ag, I think is mentioned somewhere in here about putting these things like if you end up doing an app, you could go do that. But I wanted to share that with everybody. We got a question here from Christina, so I'm going to take her off mute here. You should be able to talk, Christina.
Can you hear me?
Yes, we can.
Okay, great. Thank you so much for your talk. I was really interested by the part when you were talking about novel viruses and how, there were different communities living very close to these viruses, but they weren't being infected. And I was just curious if you could speak more to any findings that, if you have them, as to what these differences are with these communities encroaching on the environment and still not being infected, and how that compares to the zoonosis that does occur.
That's a great question. So certainly there is some analysis that is actually currently under review. The paper is currently under review, but the summary of that particular work is we did see an increased presence of these viruses in communities that are closely are involved in some kind of value chain with respect to these wildlife populations. So that are closely living in areas where there is, let's say, wildlife markets, smaller, larger, whatever type of them, or even in areas where there is large scale agriculture. So those were the two findings from that particular model. However, just keep in mind that this was very much a targeted surveillance. So we actually did, so it's not a comparison between whether the risk is greater in those communities versus communities that are not involved in those activities. We specifically went to those communities that we think that might have higher risk. So that has some limitation in terms of the interpretation of our results. And similarly, not just the number of viruses, but the diversity of viruses who are higher in those particular communities too. So, yeah.
Thank you.
Looks like maybe Jennifer might have a question.
There is another question in the chat as well. I think it was just sent to me privately, but I can take that after Jennifer's question.
Hey, Jennifer. We can't hear you, Jennifer, but you're off mute. Oh, we lost her.
No worries. Yeah, the question here from Dr. Bhatkar is, do you plan to use digital twin or virtual twin technology for prediction? Yes, I think we are moving to that direction. Certainly, there are some AMR related models, even in livestock, that we have built that we can expand to build a virtual or a digital twin, basically for not just AMR transmission, but other transmission transmission of other pathogens. especially in dairy industry, because we do have that data better represented here in California, at least in some of my collaborators. So certainly, yes, digital twin is a exciting proposition.
And if you have some other people that are on this call that are interested in working with you with terms of dairy data or other data, just reach out to you via email.
Yes, yeah.
Very good. Any other questions here? I know we're bumping up the time. Some people are probably getting hungry. I don't see any more, but what a fantastic talk. I really enjoyed it and learned a lot, way above my pay grade, but I enjoyed it as learning as an economist. I want to kind of learn everything I can as we're entering in this space. Again, if you're on the call and you're interested in submitting a 1-pager or 2-pager on bird flu, we would love to have it. And then just a further note for anybody on here, the White House issued a new NSM. It's NSM 22 on critical industries, which food and ag are mentioned in, and the additional funding and work that needs to be done in that. So this is a recognized activity at the national level, not just on our land grant institution. So it's really important that we continue to do good work, and doc work like yours is very important, and we appreciate it. So thank you again. Thank you to everybody. And we hope you have a wonderful rest of your day.
Thank you.
All right. Bye.